Hi everyone! Welcome to our project. This is Addison Lee. My project partner is Shiyiran. We chose to work on the cancer image detection because we're both very excited about this technology and its ability to assist doctors making better cancer diagnosis for the patients. So in front of you right now is the main outline of our demo today. As you can see, consists of 4 main parts. First and foremost, we're going to give a brief high-level summary of our model performance. We're then going to share our key results and experiments, followed by how we evaluated the performance, and lastly, we will walk you through the main parts of our code in great details. Let's get started. So our final model is a transfer model with pre-trained VGG16 on ImageNet with 2 simple dense layers. Since VGG16 takes the input size of 40 by 40 by 3, we sliced our original image into patches of this shape. We chose to work with the image on level 3 because it gives us enough depth as well as good granularity. Our model was able to reach 87 to 89% precision rate after 10 epochs. Here is an apple-to-apple comparison. On your left-hand side is the original slide with the ground truth tumor mask, and on the right-hand side is the prediction mask on the test image 110. We can see that our prediction was able to capture the entire cancerous region with pretty high precision. But obviously, this does not come easily. Along the project, we went through lots of trials and errors. Only after many rounds of experiment, endless crashes, and lots of coffee, we were able to tune a model that works well for us today. Our experiments included 4 main parts: selecting the right model to work with. We tried to find the right dimension level for the image. We tried the different patch sizes ranging from 10 by 10 to 299 by 299. We also evaluated the quality of training data using different sampling methodologies. So these experiments helped us to evaluate and eventually reach the model we wanted today. So let's break it down one by one. From the model selecting standpoint, our main conclusion was consistent with the paper. That is that Inception v3 does not generate a significantly better prediction. Using the features from a classic VGG16 was able to produce similar prediction accuracy with a much simpler architecture. Using transfer learning in our case does not contribute to the prediction accuracy, but helped to speed up the convergence. And secondly, select the right dimension level is also a key component to get the training images right. The ideal image should give us enough details of the tissues and cancers while not being too granular or computationally expensive. So we started on level 7, moved to 6. However, neither of them gave us the necessary depth that we needed to produce accurate results. So when we adjusted down to level 3, we reached a desirable level where our prediction precision was much higher, and our visualization was much more accurate as well. We also played around with the patch sizes ranging from 10 by 10 to 299 by 299. Initially, we started with the small patch size as 10 by 10 because we naively believed that smaller patches were able to examine the slides more carefully, therefore lead to potentially increasing in precision. However, it was simply too small. It doesn't do the job. So it confused the model and predicted a lot of benign patches cancerous. And also, it took a very long time to converge. We then tried the suggested patch size 299 by 299 according to the paper. Our prediction accuracy was also pretty sad. So our training image 091 was already relatively small at the level 3. So when we cut it into 299 by 299 patches, it was simply not enough data for the model to learn. Therefore, the poor performance was due to the insufficient input images. If we have enough storage and the computation power, we could consider using the entire Kalman dataset and then the patch size of 299 could work. But due to our hardware limitation, we only used one image as training data this time and eventually decided on the patch size of 40 by 40, which worked pretty well for our VGG16. Lastly, we noticed that the quality of the training data is vital for ensuring the model quality. When we fed the original image as is directly into the model learned a lot of non-cancerous patches because they are the majority. So the majority. So our model tended to predict every patch healthy. This would be terrible because it predicted a lot of false negatives, meaning that we failed to detect the cancer. We realized that it is quite important to have a balanced data set where the model has enough cancerous patches to learn. So we designed two methods to ensure the data balance. The first method was downsampling, which keeps all the cancerous patches and throws away some healthy patches to reach our target ratio. So take our training image 091 as an example. This method left us with about 500 cancer patches and 1,000 healthy patches on level 3. So if this method worked, it could reduce our computation significantly. However, the prediction performance was simply heartbroken. We suspected that 15 images probably were not enough for the model to learn. So we then designed an oversampling method which randomly samples from the cancerous patch pool until we reached the target ratio. We kept all the non-cancerous patches. So this drastically increased our prediction accuracy and allowed us to predict with consistency and high precision. We experimented a few ratios and finally decided to split the training set 50-50 with the tumor and non-tumorous patches. In this case, it gives the model enough data to learn without any bias towards either patch. So that summarized all the experiments we ran. Next, we're going into the details of our code. Here's an overview. So after we select the right model to work with, we started to prepare our training data. We then prepare the testing data. We train the model, make the prediction, print out all the evaluation metrics, and then finally display the visualization. We wrote all the utility functions into small blocks to assist all the tasks that we need to do and to minimize the code repetitiveness. So here is preparation work and utility functions. We prepare the training data by writing a few small functions such as reading the slides, detect the tissue patches, assign the labels to each patch, and then this function to get us the patches we wanted. This function is the key to cut the original slide into desirable patches. It takes 3 parameters: the index number of the image we're going to read, the size of the patches, and the level of the slide we will be working on. Since the image will be cut into patches of 40 by 40, the key here is to identify the right x and y coordinates of each patch. And we computed the coordinates by multiplying the step size, which is also the patch size, the downsampling factor of the image at level 3, and then the loop index. It returns 2 arrays, one array of the patches that we wanted, and then the other array of the labels correspondingly. After getting the right patches, we normalized our data. Here's the normalization function. And then we oversampled right here. We oversampled the cancerous patches to make sure our training data set is balanced. So the oversampling function takes the training data and labels, randomly select the cancerous patches until the volume of cancer patches catches up with the healthy patches. Then the function returns the data set filled with 50% healthy patches and 50% cancerous patches with their corresponding labels. And that is how our training sets get ready. We then prepared our testing data, which is much easier. We simply read the test image through the slicing function, normalize it, and then they're ready to go. The natural next step is to train and test the model. Here's a simple function we wrote to use the transfer learning to build our model. This function simply takes the base model as a parameter, added a couple of layers, and then output the model for us. And then here's the train and predict function. After training and testing, we printed out all the major metrics we used to evaluate the performance by calling the evaluate function. So you will see such as losses, precision rate, confusion matrix, and etc. Last but not the least, for a clear visualization, we plotted the original slide with the ground truth mask against the slide with the predicted mask for a direct comparison. Here is the helper function for us, helper functions to help us get the slide, get the mask. The label to image function is the key here to get the plot right. In order to stitch the patches back correctly, we need to pay attention to two things. The first one is to get the order of the row and column correctly. And then we resize the prediction mask back into the exact same size as the original slide. And then this small function just helps us to visualize the test image directly, and then eventually we put them together to compare. Here is how we executed our code. As you can see, this follows the steps of selecting the model, prepare the training data, oversample the training data, preparing the testing data, train and test the model, print out the evaluations, and plot the visualization. And here is the summary of our model, a history of the training, and the evaluation results, and eventually the visualization in front of you side by side. Oops, where did it go? All right, here we go. So we can see that our prediction was able to capture the cancerous areas pretty precisely. We believe that if time and resource permitted, we can add in better data augmentation. And additionally, by enlarging the training size, we expect to achieve higher precision rate. We understand that detecting cancer and using deep learning in any medical settings in general is a huge responsibility. We should keep in mind that this is better suited as a secondary validation followed by an initial assessment of an experienced doctor. So this is our project. We hope you enjoyed this demo as much as we enjoyed working on it. Thank you very much for an amazing semester and happy holidays. Cheers!